Hello, this is Jette Wagen and welcome to this final session of this 4-session screencast on drone archaeology. Now this final session will be a practical session. This is intended to show you in a step-by-step guide how to post-process visible light photos from a drone mission using photogrammetric software. The photographs that we will be using have been collected at Siggerswoude, which is an archaeological site in Friesland in the Netherlands. Now Siggerswoude is an archaeological site known to local farmers. It is also visible on satellite images and LiDAR data, and it takes the shape of large rectangular plots defined by ditches that encompass a surface of around 1200 square meters. Now one of these plots is clearly visible, as you can see in the aerial photograph in the right lower part of the screen, and the existence of others is known or can be deduced from historical sources that probably relate to a late medieval project to cultivate the soil. Now the objectives of the drone operation here have been to test the methodology and techniques for drone photogrammetry, to result in a very detailed archaeological mapping of the area, and to research the results of modern agricultural land reforms. Okay, so for this practical we will be working with Pix4DMapper. As I mentioned, there are various software packages for photogrammetry, but I chose to work with Pix4D because it's quite user-friendly. I really like working with ground control points in Pix4D, and at the moment it also has some advanced features for working with thermal and multispectral data. So what we will do is go through the basic steps of processing orthophotos collected during a terrain mapping mission. So this is not an oblique capturing strategy aimed at a 3D structure, but a low oblique landscape capture approach. Now we'll first start with the inspection of the data that we got from the SD card of the drone. So what we have here is a series of photographs, 160 items in total, that have been photographed from an altitude of 50 meters with a speed of around 3 meters per second and an overlap suitable for photogrammetry of 80% frontways and 70% sideways. Now if we look at the photos, we can see that this results in a series of nice overlapping photos taken with a low oblique camera angle, so the camera is not pointing straight down but at a slight angle to the ground, which results in a good capture of 3D shapes of the terrain in the resulting photogrammic geometry model of the terrain. Now this flight was performed using a regular meandering pattern, and of course ground control points have been laid on the ground for the referencing of the dataset, and here you can see the targets in the drone operation area. Of course these targets have been measured, and I have been recording these and exporting them from a differential GPS system X, Y, Z coordinates. So this is the basic set that I need for the drone data processing in Pix4D. So back to Pix4D then. I will start with explaining the interface. In the top we have our menu. The first item in the menu is the project menu, which offers us the usual options of creating new projects and saving them, but also view and define properties of images, ground control points, and output coordinate systems. Then we have the menu item process, giving access to all processing options and actions. Then we have view, giving access to different views of the software, and then we have the help menu. Now below then we have a toolbar presenting quick access buttons to options in the menu that I just introduced. On the left we have the view toolbar that allows switching between map view, Raycloud view, volumes, Mosaic editor and index calculator. Depending on the state of the project, these buttons may be grayed out and become available during processing. Finally, left on the bottom we have the processing toolbar, presenting buttons for showing the processing bar with which you can make the processing toolbar appear, make the processing log appear, and access the processing options. Okay, and then here in the center, this is the home view, and we have here a set of project options. For this new project, we are going to select New Project. If we click on that, we will make the New Project wizard pop up, offering the option of a new project or to merge existing projects. And the latter is of course useful in case you had to split up a job processing in several parts. Now clearly you are required to enter a name for the job as well as a location where the project will live, and I will do that right now. Now, after clicking next, you are prompted to select the images that you want to use for the job. Here you can select batches of images or simply point to a directory, and Pix4D will try to add everything in that folder as a camera to the project. Another option is to add video, which is a useful tool in case you were not in control of the recording session and you only received a video output. This option will then allow you to automatically extract frames from those videos and use those frames as individual cameras. We will add the images now. After selecting all the images, you click Next, and you will see that Pix4D will try to automatically detect the camera rig and present you with the image properties window. Now the image properties window consists of two boxes and a list of images. The first box here is the image geolocation box. You see here, and this is a standard in Pix4D, the green check mark communicating that Pix4D expects no issues with this item. Now first of all, you need to check if the selected coordinate system is correct. This refers to the GPS location that is stored in the EXIF part of the images, the metadata, and in my case should indeed be WGS 1984. It tells me that all 160 images are geolocated, and below I can define the geolocation accuracy. You can set it at standard, which means that you expect a maximum error of 5 meter horizontal and 10 meter vertical. You can set it to low if you expect the geolocation to be very inaccurate, which will set it to 50 and 100 meters respectively. Custom allows you to specify custom accuracy, and if you would have different sets of images with different accuracies, you can use these settings to define a hierarchy for Pix4D for using only a specific set with accurate geolocation for the initial processing phase. In the box you will see the identified camera rig with this specific icon over here, telling us that the camera model is actually stored in the camera database of this software. It may also be extracted from the EXIF data, which will then be indicated by a different icon. Detecting the correct camera rig is important as it will help Pix4D have the correct geometrical understanding of the relationship between the camera and the scene. Important parameters are, for example, focal length, imaging size, lens distortion, etc. If the camera model is unknown, this is likely to lead to processing errors. The Edit button here allows you to create a camera model. The camera model you see here indeed is the Zenmuse X5S that I used for this mission. Then we see the list of added images. And I will enlarge it a bit to show all the different columns. And this shows every single image with their geolocation, estimated accuracy, and rotation around the X, Y, and Z axis of the gimbal. As you can see, the altitude is completely off. This has been a flight at 50 meters altitude. Now one may expect some GPS inaccuracy, but minus 35 meters makes no sense at all. Now this source of errors appears to be located somewhere in DJI's firmware, where an erroneous set value is attributed to the images and Pix4D can't do anything about it. This may be unfortunate, but it gives me the opportunity to show you how to deal with it, which you can do by simply editing the field value. If you right click on any specific field, you get the option to edit all altitudes, so to edit all these altitude property of all images. So we click on that, we change this to 50, we click in the next field, and we see the altitude for all images change to 50 meters. So with this we have verified that all the image properties are okay, and we can click next. Now we are presented with the output window. It allows us to define in what coordinate reference system we want our output to be projected. For the output and the ground control point coordinate systems, we need to set the correct system. In the Netherlands, we commonly work with the Rijksdriehoekstelsel, which is the projection that we will use in GIS to compare the drone data to other data, but moreover our recorded targets have a Rijksdriehoekstelsel coordinates as well. So we set that to known system and then check advanced coordinate options to be able to search for the correct projection. Now you can search using various approaches, but I find it easiest to just select the correct EPSG. And in this case, I know the number that I need to have, and I will scroll to it. And there we have it. This is 28992. Okay, which is the RD new system. Then we click next, and we are presented with the processing options template. This is something quite useful as it contains templates that are already pre-configured sets of processing options that are optimized for specific goals. Of course, all these options can be and should be reviewed critically during the process itself, but this nonetheless can save time. There are standard options, rapid options that produce fast outputs for quality checks, and advanced options for more specialized applications. The AG templates are specifically for missions for agricultural purposes. Now we will choose 3D maps over here, because as said, the mission was specifically aimed at creating a 3D map using a meandering pattern of low oblique photographs. Best do not check the Start Processing Now box, because you usually want to review your data and processing parameters first. So we will click Finish, wait a bit, and now we will see the 2D map view activated over here. Here you see the GPS locations of the drone photos and the green line that indicates the flight path of the drone. These are projected onto a satellite photograph as a background map. The red color indicates that the images have not been calibrated yet. In order to check our ground control points, we can now also import them. So in order to do this, we go to Project, GCP MTP Manager, and MTP means Manual Type Point. And if we click on this, we go into this window. Now here we double check whether our GCP coordinate system is the right one, and indeed it is. And then we will click on Import GCPs. We check if the XYZ is in the correct order, and then we click Browse. We browse through our list of coordinates and click OK. Now you see a list of coordinates, and you can check if they all seem okay. Well, we have an X, a Y, and a Z value, and they look like they are correct, so that's fine. You also now have in the lower part of the window direct access to the GCP or MTP managers or editors, the basic editor and the Raycloud editor. The Raycloud editor is specifically effective, but not yet available as we do not yet have a Raycloud. For now, we'll accept this and click OK. Alright. We now see the ground control points added as blue crosses in the mapping area. In this way, we can easily verify whether all the reference data is actually correct. By the way, you can clearly see that we actually mapped a larger area here, which we cut partly to avoid a too large dataset for this practical demo. Now we can also go to Raycloud view. This is the view in which we can inspect our data in 3D, and the layer panel appears that shows the different types of data that we will be able to display. Now this is called a Raycloud view, as one of the very useful bits of information that in this view will be rays indicating relations between selected 3D points and the cameras, but this will become clear later. Since the cameras have not yet gone through initial processing, we do not see their location projected in 3D. So let's start with the initial processing. This is the phase in which the images are inspected on unique key points, which are unique locations on the cameras defined by things like a high contrast. These key points are then compared to key point sets from other images. If they match, they produce so-called tie points, which are matching locations, exact locations between images. By applying geometrical calculations on sets of tie points, their relative position in 3D space can be calculated, after which the external calibration of the cameras can take place, which means that the original location and XY set orientation of the lens at that moment will be reconstructed. After this step, we can inspect the result, use the GCP for correct referencing, and then can proceed to step 2 and 3, which produce the point clouds, orthophotos, elevation models, and 3D models. If we click on the processing options, we can review the options for step 1. The processing options are primarily organized by the vertical lab on the left, and you saw me unchecking step 2 and 3, as we will be dealing with those in a later phase. You may check the tab Resources and Notifications and modify the resources allocated to the processing, as you may want to be able to do other work on your computer at the same time as processing. I will leave this all at maximum to process as fast as possible. Now for the tab of phase 1, we are presented with 3 horizontal tabs: General, Matching, and Calibration. General we set to full. The key points image scale here refers to the degree to which images are computed on different scales, with more scales allowing for more key points to be extracted and thus more accurate data, and less scales the opposite. As with many of the processing options in photogrammetry software, the choice is between processing time and quality, although there are always tipping points at which the increase of quality is nihil or negligible, but the processing time is increasing exponentially. It is very important to gain some experience and knowledge here to understand what is useful and what not. Important to know is that with low resolution images such as thermal images, a double scale that you can set here under custom can be useful for more effective key point extraction. However, as I said, for this project we leave it at full. And then there's the option of quality report, and it's definitely recommended to check the box because the quality report is important for inspecting and interpreting the results. Now for the matching tab. In the matching tab we can choose which pairs of images are matched and how they are matched. The image pairing is important, as an increase in the number of images that are compared will increase processing time significantly, where it is of course useless to have Pix4D analyze images from either end of a field for matching points. The option Aerial Grid Recorder is standard selected in this template, as this setting assumes a regular flight plan for selecting nearby images for pairing, whereas free flight or terrestrial won't and thus compares more images. The other settings under custom allow you to specify other variables for creating pairs, such as capture time, which means the less time between images the closer they probably are, or geolocation GPS coordinates, or distance, which is more useful if there are large altitude differences between images. The option Geometrically Verified Matching finally adds an extra quality check that slows down the process but can be useful when errors are expected, for example as a result of repeating patterns. In this case, we leave this unchecked. Now then the calibration tab. What we can set here is the targeted number of key points, which is fine at automatic, but can be customized in case of bad results. You can increase the number of key points, or in case of long processing times, you may want to decrease the number of key points. The calibration method is set to standard, but can be changed to alternative, which is faster for pure nadir datasets and flat terrain, and accurate geolocation and orientation, which is only useful if you have an RTK enabled system or similar. As for the camera optimization, the internal and external parameters, we set them at all, which is useful for most setups because it optimizes all parameters which are usually affected with drone photography. The other options are suitable for less common cameras. Rematch then allows for adding matches after a first round of processing, which is only automatically done for projects with less than 500 images, but can be set here for larger projects as well. Pre-processing then is only relevant for specific drones, and export camera internals so they can be used for reoptimization. So we check this one. So having reviewed all the options for the initial processing, we click on OK and we click on Start. Once you click Start, you can monitor the progress. The dots will change to a green color, which indicates that they have been processed. After this phase, you will see switching light blue dots that indicate where matching points, tie points are found between images. The dark green points eventually indicate calibrated cameras. In other words, cameras that can now be placed in 3D space. Now, this will take a while, so we will skip forward to see the results of the initial processing. Okay, so after the initial processing is finished, you will be prompted with the quality report. Now, as I just loaded an earlier saved file in which the initial processing already been done, I am not being offered this quality report. However, of course, it is already generated and we can find it in the project folder. So we will first go through the quality report because that's typically the first thing that you should read before the more detailed inspection of the results. And the quality report can be found in the project folder. So here I have these various project folders and this is the initial processing. I click on it. This is where this project lives. I have here all the data that has been outputted as the first step, the initial processing step. I click on that and here I have 3 folders: params, project data and report. If I click on that, I can here find the PDF with the reports. And there it is. So we will check this report in detail. There's a lot of useful data in this report, which is most helpful in case there are large errors in the output. However, we will now inspect a few key values that can tell us a lot about the quality of our project. So what you can see here is a summary of our project. Again, we can see the area covered, the camera model, and an important thing to always check is whether the ground sampling distance is actually the value that you expect, which it is. Then we will do a quick quality check. In this table over here, we can see that the 4 out of 5 entries for the quality check show the green check here in the end. So we successfully generated a median number of almost 86,000 key points per image. We calibrated all images inserted into the project. We have a median of almost 22,000 tie points between the images, and the only exclamation mark is there because we did not yet reference the model to the ground control points. Now the preview over here also presents us with a good visualization about on which we can check the quality of the data. And here again we can see no great distortions or weird things. Now we can check all the information in all the informative tables and graphs that this report presents But again, as long as the quality markers are okay, you basically don't need them. A final quality index that you should check, however, is the reprojection error. Now, the reprojection error is an important quality indicator, and you can find it here with the bundle block adjustment details. The reprojection error is an internal error indication. This is derived from reprojecting the 3D points in the 3D model, which is the result of a calculation, of course, back onto the calibrated cameras. Now, in case of errors in the photogrammetric process, these points will not fall back exactly on the correct place. The root mean squared error of all these reprojections combined gives us an average estimate of the quality of the model expressed in pixels. Now we can see here that this is about 1/5 of a single pixel, so we need not worry. Now this quality report will be expanded in further steps with the results of further processing. But this is the essential phase in which we really need to check it and decide whether it's acceptable to proceed or whether we need to fix some problems. Now we clearly concluded that this is a fine result, and we'll go on to the next phase, which is the referencing. Let's first check the 3D data that we have. What we can see over here is that the cameras are represented by blue and green spheres. The blue represents the original camera locations, and the green spheres represent the calibrated camera locations. If you click on a blue camera, you will see a line connecting it to a green sphere, which is not very easy to see, but here you can see the small line that indicates the connection between these two. The squares are then displaying thumbnails of the corrected images. If you click on a camera, you will also see that the camera is selected in the panel to the left, which is of course under the menu item or the layer item cameras and then calibrated cameras. And to the right, you will see a panel displaying the properties of the camera, such as the exact position and rotation, as well as the number and location of the identified tie points over here. Now below the cameras, and you can uncheck the box in the layers panel to hide them in 3D view, you can see the ground control points and the tie points projected in 3D space. And the tie points are also known as the sparse point cloud. Again, we do not see any weird things, for example, substantial group of tie points above or below the plane which represents the terrain surface. The ground control points, however, are projected somewhat higher. This has to do with the fact that the absolute positions of the tie points are determined by the GPS coordinates, which are known to deviate more substantial in Z values than in the X and Y value range. Now finally, and this is why this is called the Raycloud view, we can switch on the cameras and click on any tie points and see a number of rays that appear to show one green rays connecting 3D points to the cameras on which that point was visible but not marked, and two orange rays connecting 3D points to cameras on which that point was marked. Now it's time to start with the referencing. If you click on any on the ground control points that overlap with the sparse point cloud, you will see green rays indicating on which image that location should be visible. You will also see the selected ground control point in the layers panel, and we see its properties to the right, showing the coordinates. Below these properties, we get a selection of images in which the point should be visible, determined by these rays. This is a very convenient feature as it makes it very easy to identify the targets on the images and connect them to the correct ground control points. The process is now one of systematically specifying these connections. Start with one ground control point and start inspecting the images in the list over here. You may notice that these targets are actually targets derived from Agisoft Metashape that has a feature of printing out your own coded targets that would then be automatically identified. After this flight operation, I switched to Pix4D that does not have this feature. So I use these targets, but in the end they are not really useful for this particular piece of software. The codes are rather vague because in the field I decided to fly a bit higher than optimal for the recognition. Now, if I would have known this beforehand, I would have probably chosen different markers with more clear intersections of blue and white squares, but in any case, in this context, these will do. After all, I only want to use them for general georeferencing. So what you do is you inspect the images and you click on the location in the center of the target. The blue crosshair over here indicates the current position of the ray intersecting the image. So I will identify as best as I can the center of the target and click on it. The yellow circle here represents the accuracy of the indication. The more you zoom in, the smaller the circle becomes, so you can use this to indicate how accurate you think the position is. If you are less sure, zoom out more, and this information will be used in reoptimizing the image. Now, after identifying two of these points, you will see green crosses appearing, which indicates the calculated position of the ground control point based on the already specified points. Now, after identifying a few of these points on several images, click Apply. You will now see a few things happening. The orange rays now show the established connections. You will also see a green ground control point projected onto the correct sparse point cloud location. Now proceed with the other points, and after defining a few of these in the menu options, choose Reoptimize. Now Reoptimize recalculates the internal and external calibration of the cameras and can be done at various stages after adding information to the project of which you expect the results could improve. If you think that the added information could also result in more matches between images and improve the model quality, then the option Rematch and Optimize should be chosen. Now again, I will not go through all of these steps, and I will now open the file in which I already corrected around 6 ground control points and then run the Reoptimize function. Now after this step, you will see that the sparse point cloud has been corrected and the ground control points now accurately fall on its surface. We could localize all ground control points. But if we click on a projected one, a blue ground control point, and we zoom in on the images, we can now see that they have been located quite okay. The errors which there are not to the degree that we worry about it for our archaeological application. If we would worry about it, we would continue until all is as perfect as we can get. But that in this phase is not really important, or in this archaeological application I would say. Now we will regenerate a report and check the results. We can do that going to Process and here generate a quality report. This will take some time because Pix4D will need to load some information for this, but we will wait for the report generation to be finished. Okay, so once this quality report has been generated, we are prompted with the HTML version of the quality report, And we can now quickly check what the ground control has done for us. The first thing is that we now have a quality check with 5 entries, and they are all 5 have green checks on them. What we can then see is that we have 6 ground control points identified, and there are 3D ground control points, and their mean root mean squared error is 0.011 meter, so 1.1 centimeter error on average. Now this is an error that we could fix if we want. In this case I don't worry about it, as I said earlier, but if I would be making a very highly precise, accurate model of an excavation, for example, or I would be working on a 3D documentation of a structure, then I may want this to be even smaller, this error. In this case, I am not worried by this error, and I will consider it quite acceptable. Because in the end, this is a remote sensing job, and this error does not make any difference in our possibilities to analyze the data. We'll check also the reprojection error to see if it increased, decreased, or basically stayed the same. And as we can see, it decreased by a negligible amount. But the important point is that it didn't suddenly increase or something. Now, actually, after this point of generating our sparse point cloud, making sure the reference is okay and the cameras are calibrated, the rest of the process is just basically one of processing an indicator, defining in Pix4D the products that we want out of the software and let it work on it. So the next steps would be to go to step 2, which is the generation of the dense point cloud and the mesh, and step 3, which is the generation of a digital surface model, an Orthomosaic and Index maps. So it is time to check the processing options again. We can uncheck step 1, which we did, and go to step 2 and look at the new horizontal tabs that appeared. First of all, we have point cloud. So for the densification of the point cloud, the software generates depth maps of all images and projects those points in the images into 3D space. This densifies the points, which are then used to generate the 3D mesh and orthophotos, etc. Now for the specific options then, with image scale over here, we determine if we want all images to be projected full, or whether we want them scaled down a bit to avoid an overly heavy point cloud. Multi-scale here means that you can calculate on all scales, which can be effective for creating additional 3D points where there is more detail such as vegetation. The point density then determines the scalar for the actual pixels. Optimal is 1 point for every 4 pixels, and thus 8 in case of the default half size. But you can also go for high for every pixel or low for every 16th pixel. As mentioned earlier, this is all processing time versus detail. Then you can also set a quality indicator with minimum number of matches, where you could say that a point can only be used if it can be successfully projected on an X number of images. Point cloud classification then can be useful, certainly if we expect many elements distorting our point cloud, such as cars, trees, or buildings, and we want to be able to remove them, or we want to create separate models or GIS layers for those items. Now this option, if checked, uses an algorithm that classifies points belonging to such elements. Then for the export options, in case you would want to process the point cloud itself in other software such as Saga or Cloud Compare or Lost Tools, here you can get different formats in your output folders. So then here we have the tab for 3D textured mesh. The first checkbox allows a choice whether we want it, and then we can adjust the settings. So here a 3D mesh consists of triangles, And in 3D terminology, these triangles are called faces. And these are derived from the PC using algorithms. So the visual information of the images then is projected onto the mesh as a texture. Choices relating to the texture are whether you want a high, medium or low resolution, or whether you want to customize the texture quality, varying from setting the exact texture size to specify decimation criteria. Finally, for further processing in 3D software environments, different export formats can be chosen. Then finally, we have the advanced options for the previous settings. The matching window size is the size of the grid used to match the points in the original images. With the image groups, you can determine which image groups, if you have more than one group, for example a group of visible light cameras and a group of thermal cameras, should be used for either the mesh geometry and the mesh texture. Then there are the point cloud filters that can be taken into account for processing the point cloud and mesh, which are processing area annotations with which you can mask areas or limit the camera depth to avoid reconstruction of background objects. Finally, there's a sample density divider for the 3D mesh, which can be used to create more triangles in regions with a low density of points and can fill up holes in a mesh. Now, in fact, all these settings are fine for me in default mode. I can use them directly and I will start the process. Or at least you should start the process, and I will now load the finalized version because this can take quite some time. Okay, so the point cloud and mesh processing has been done. I want to inspect all the results at the end, so we will immediately proceed to the generation of the digital surface model Orthomosaic and Index. But of course, depending on what you want from the photogrammetric process, you may not be interested in the orthophoto or the digital surface model. However, if you select this step, again you will see 3 horizontal tabs appear, and we'll go through the settings. Okay, so for the digital surface model and the Orthomosaic, what we see is the resolution that we want to set the resulting orthophoto and surface models, which standard is 1 ground sample distance, but you can set a custom resolution. Specifically for the digital surface model, you can then remove noise, which means outliers, but this will not affect the point cloud, just the resulting digital surface model. Then you can apply local filters to smooth the surface with the choices to preserve sharp features, smooth them, or something in between. You can check the box if you want the digital surface model to be actually generated and choose the method. Standard is inverse distance weighting, which is an interpolation algorithm, but you can also use Delaunay triangulation that is faster but can create problems when there are more complex 3D features in the model. If you uncheck merge tiles, you will have a digital surface model consisting of separate tiles. Finally, the Orthomosaic box must be checked if you want it. The merge tiles is similar as just explained with the digital surface model. And with the geotiff without transparency, the areas of the raster that contain no data values, in other words, there's no data available for those pixels, are black, instead of that they hold an instruction to have GIS programs not display those pixels. So it's always good to leave it at geotiff with transparency for most purposes. And then finally, it is possible to create Google Map tiles and KLM files for use with Google Map and Google Earth. Then on the second tab, we have additional outputs. For example, if we want to generate a vector version of the digital surface model, we can choose here several output formats. In the next box, we can select to have Pix4D generate a digital terrain model, so a digital surface model from which all the buildings and other objects have been removed. For example, those classified as non-ground in the point cloud classification step. Again, we have the merge styles option and the possibility to set a specific resolution. Finally, contour lines can be produced, for which you can choose either one of these vector data formats. And then you can set a contour base, which means an altitude to start from, an interval, for example, a contour at every 5 meters, a resolution on which you want the evaluation to be calculated, and thus forms a smoother line if this area is smaller, and a minimum line size to be able to avoid small lines creating a lot of noise. The last step then is index calculator, which are settings that are only relevant for dealing with multispectral and thermal data. Options here are to deal with optimizing the radiometric quality of the data, define resolution, and determine whether a reflectance map and or indices must be generated. And so again, I'm fine with the default options. I will click OK and I will click Start again, and it will start processing, and again can take quite some time. So instead of actually doing that, I will now load the finalized version of this project. Okay, so here we are, and we now have all the products generated. I will now show you what we have in this project, and I will switch off the cameras, the rays, the tie points. We've all been explaining this, and I will now visualize the generated dense point cloud. So there are some visualization options here which are not really interesting to play around with too much. But as you can see, we now have this dense point cloud of points that are now represented by little squares here, and you can change this size so they become real little and neat small points, but you can play a bit with that to change the visualization. But you can see here the effect of our low oblique mapping session, because we have been able to get a really good capture of the landscape and the site that we actually wanted to capture, but we have a lot of occlusion areas here because we didn't fly low enough, low oblique enough, or made enough horizontally oriented or high oblique photos to actually capture occluded areas. And of course you have the problem of the vegetation that just doesn't allow a good view of the terrain under it. But this is no problem because that was not our intention. Now then, we could, if we would have classified the point cloud here, switch on and off different groups, but clearly we didn't do that. So if I switch off unclassified, all points disappear, but you can see here pre-made categories of classes in the point cloud that you would be able to turn on and off. So this is the dense point cloud that we generated, and then we have here the triangle mesh, so the actual 3D model generated from the dense point cloud. And this takes a bit of loading, and I will switch to the version in which this loading process is already finished. Okay, now so the loading is finished. So what we see here, it looks a lot like the point cloud, of course, but now it has been reworked, processed into an actual mesh with gaps in between, again because of these gaps in the point cloud data. And we can switch the shader here to, for example, monochrome, and then you can see the actual triangles or faces that I was just talking about that have been generated. And the textured version is then the texture from the photographs projected onto each individual face. Now there are a few other color distributions that you can use here just to see if it maybe for some reason helps you inspect your data. So you can color faces based on their relative altitudes, but in the end this mesh is much better viewed in other software. Now, if you remember in the beginning, I have been talking also about these different views. So you have here 3 more view options, which are volumes, Mosaic editor, and index calculator. Now, volumes is optimized for volume calculation. So if you want to use the program Pix4D directly for calculation of a volume, for example, of a heap of stones or something like that, the Mosaic editor then is a tool in which you can change the projection of your orthophotos, so you can directly and accurately measure on them, for example. Now these are typically actions that in archaeology we use more specialized software for. So instead of the Mosaic editor, we would just import it into GIS. Instead of calculating with volumes, we would probably go into 3D software such as Blender. So these are functions that are really useful for people that just need these functions, and so they have enough functionality provided by Pix4D. But basically in archaeology you will probably go onto different software. The index calculator, however, is very useful, but again this also can be done in GIS, and this is specifically for multispectral and thermal data, so will not be part of this demonstration. However, what I will do is provide you with some pointers to find the produced products with Pix4D and show you how to open them in respectively a 3D software such as Meshlab and a GIS package. So first of all, let's go to the hard disk. Let's see where the information, the folder, the project folder was created. So my final folder is this one, and if I open it, you can see that I now have data for each of the 3 steps. And we already saw the initial folder, so let's click now on the densification. And what we can see here is we will have 2 folders. One that will store the 3D mesh, and I opted for an export in both OBJ and FBX. So there's 2 different formats of 3D models there, and here I have a point cloud exported as a .las file format. Now then for the third phase, I have here the DSM ortho. So I have a digital surface model. Digital surface model has been exported as a TIFF file with a projection file and a TIFF world file, so it will be immediately projected on the correct location in GIS. And then finally, of course, I have the Orthomosaic, which is a similar format with similar properties. So I will now go on to open a 3D model software and a GIS package to show you how to import it and show you the final orthophotos, DSM, and the 3D model. And so I just started up a version of QGIS. It's 3.16. The EPSG here is also set to the rechtsdriehoekstelsel RD new, and via the PDoc plugin I loaded the 2020 orthophoto, aerial orthophoto of the Netherlands. Now if I go to the section on my hard drive where the project lives, I will go to the training data area, and here I have my folders with the final DSM orthophoto and index, where we just were looking directly from the Windows Explorer. I can go directly into DSM and ortho and, for example, drag the Orthomosaic directly in my GIS. Now it has been loaded. I can go zoom to layer, and you will see the orthophoto directly projected on its exact location or close to exact location. Remember the very small GCP error in the on the aerial photograph. And the nice thing is that you can see here on the 2020 photograph, you can see here the traces of the test trenches that have been dug here by the National Heritage Agency that has been excavating here afterwards. And the same thing we can do with the digital surface model. So I can directly insert it, and we will have a surface model. Now, of course, this is the effect of not filtering out trees from the dense point cloud, and so the color ramp from black to white is now completely dominated by the higher areas here that contain all the shades of gray. But if we would zoom in, for example, do a local histogram stretch, we will get a very detailed representation of the much more smaller and local contrasts in elevation. And what you can see here is now very nice that the elevation that doesn't show that well, or actually almost not on the orthophoto, but the elevation differences give us a very clear definition of a second terrain. Now this is also really showcasing the potential of drone photogrammetry, because also on the LiDAR data in this area, that square was by far not that clear. So to not go into too much details about the project itself, it is just a very nice demonstration of the added value of drone photogrammetry. Now for the GIS part, I will leave it to this. This is of course the departure point for much more advanced spatial and raster analysis, which are not part of this course. But I have shown you how you start from single images from a drone recording session and end up with very useful products such as this. Now, as the final thing, I also want to show you how you can do that with the 3D model, which you can open directly in a program, which is, for example, Meshlab. Okay, so as you can see, I already opened Meshlab. Let's open the model first because it takes some time to load. So the third button over here is the Import Mesh button. I will click on it. In my folder structure, I now go to the densification folder and then to the first item, the 3D mesh, and here I will select the OBJ file and it will load the 3D object into the program. Now, important information is that the Meshlab, just as QGIS, is an open source, a free open source software. So this is just downloadable on the web and immediately usable for free. Okay, so now my model opens, and as with with QGIS, I'm not going to go into the details of how to work with this software, but I just want to show you that you now have a very nice visualized version of the 3D mesh in Meshlab, and you can start playing around with it to optimize it, to use it for analysis, or to create nice visualizations of it. And of course you can, for example, start playing with things like lighting directions and see if it can even help you discovering more features. So this is what you can do with the 3D model directly in 3D software. And so with this final example, I've come to the end of this practical demonstration. I hope it has been useful and informative. This is the final session 4 screencast in a series of 4 screencasts on drone archaeology. Thank you for watching.